Orbiting Earth on the International Space Station, the Alpha Magnetic Spectrometer has analyzed over 200 billion cosmic rays. The instrument identifies these particles by mapping their rigidity, measuring the extent to which a particle's path is deflected by a magnetic field. This technique allows the AMS to measure particle flux with 1% precision. But that precision has created a problem for astrophysics. Recent measurements of heavy elements like phosphorus and argon contradict current models of how cosmic rays are produced and how elements move through the galaxy. In particle physics, when experimental data improves precision by an order of magnitude and breaks a theoretical model, it usually necessitates the discovery of a new physical property. To understand how physicists will resolve the AMS anomaly, we have to look at an earlier mathematical paradox that forced the invention of quantum chromodynamics. The delta++ baryon consists of 3 up quarks, all possessing parallel spin. Because the delta++ is the lowest mass state for this specific baryon, its orbital angular momentum is 0. The total wave function factors into the product of 3 components: spatial, spin, and flavor. Because these are all symmetric, the total resulting wave function is also fully symmetric. But quarks are fermions, making this a direct contradiction of the Pauli exclusion principle. This left physicists with a choice. Either the model of fundamental particles was incorrect, or it was missing a hidden property. In 1964, Greenberg, Hahn, and Nambu postulated a solution, an antisymmetric internal degree of freedom called color. Under SU3 symmetry, quarks exist in 3 states: red, green, or blue. The mathematical framework for this symmetry is defined by the 8 Gell-Mann matrices. The diagonal operators, lambda-3 and lambda-8, define the new quantum numbers of color isospin and color hypercharge. To account for why these properties aren't seen in isolation, the theory established color confinement. All freely observed hadrons must be color singlets, where the total color isospin and hypercharge sum to 0. While SU3 color symmetry restored mathematical order and protected the Pauli exclusion principle, it remained theoretical until it could be measured in a physical experiment. Proving the color postulate required an electron-positron collider. The baseline interaction is an electron and positron annihilating to produce a muon and an antimuon. This is compared to a second process, an electron and positron annihilating to produce a quark-antiquark pair that then forms hadrons. At high center of mass energies, the amplitudes of these 2 processes differ only by the electrical charge of the final state fermions. By dividing the cross-section of hadron production by muon production, we arrive at the R ratio, a numerical prediction that can validate the color postulate. We can calculate the theoretical R ratio for a collider with a center of mass energy of 6 GeV. At this energy, the up, down, strange, and charm quarks are all available. Summing their squared electrical charges results in 1.11. If quarks exist in 3 color variations, we multiply this by 3, resulting in a prediction of 3.33. The historical collider data allows us to compare this calculation against empirical reality. At the 6 GeV mark, the physical data aligns with the 3.33 prediction. The alignment of physical measurements with the theoretical prediction of 3.33 validated the existence of the color quantum number as a fundamental property of matter. This factor of 3 also correctly predicted the decay rate of the neutral pion into 2 photons, further validating the model. High-precision collider data established quantum chromodynamics by forcing theoretical models to match the empirical results. This same process is now being applied at the scale of the universe. AMS measured phosphorus, chlorine, and potassium, elements with an odd number of protons, and found they contain a higher proportion of primary cosmic rays than models predict. Traditionally, these elements were thought to be produced almost entirely by interactions in interstellar space. The AMS data suggests instead that significant production of life-critical elements occurs during cosmic ray interactions within the galaxy. Just as collider anomalies proved the existence of color, the precision of the AMS is currently being used to build a new model of how matter is synthesized and distributed across the universe.